Hi, I am Arib. You are watching my YouTube channel. Difference between lightning arrestor and surge arrestor. Introduction. A steady electrical supply keeps modern industry running, but it's vulnerable. Lightning strikes or sudden internal switching can send dangerous voltage spikes through the system. The spikes don't just damage equipment, they can shut down operations and create real safety risks. To protect against it from happening, we rely on surge arresters and lightning arresters. But people often mix up these two terms, and it may have lead to the wrong kind of protection. Yes, they both shield against overvoltage, but each deals with a different problem. Knowing exactly what each device does matters. That's how you build an electrical protection system that actually works, one that keeps operations moving and equipment safe for the long run. What is a surge arrestor? A surge arrestor is a device designed to protect electrical equipment from transient overvoltages or electrical surges caused by switching actions, lightning strikes, or other sudden disturbances. These surges can damage sensitive components if not properly diverted. Surge arresters operate by offering a safe path for surge current diversion, preventing it from reaching the connected equipment. Surge arresters typically use metal oxide varistors, MOVs, to clamp transient voltages to a safe level, ensuring that electrical systems remain stable. They are commonly installed in low-voltage and medium-voltage systems, offering protection for telecommunication towers, consumer electronics, and industrial machinery. Surge protection devices, SPDs, are often used in these applications to protect against the risks of electrical surge damage. Surge arresters are designed following standards like ensuring their effectiveness and safety under international guidelines. What is a lightning arrestor? A lightning arrestor, on the other hand, is primarily designed to protect electrical systems from the direct effects of lightning strikes. When lightning strikes, the arrestor provides a low-resistance path for the lightning current to be safely diverted to the ground, preventing the system from being overwhelmed by the surge. Lightning arresters are often found in high-voltage systems, such as those used in power transmission lines, substations, and industrial plants. They are equipped with a spark gap or air gap to handle the intense flashover voltage caused by lightning. Unlike surge arresters, which are used for smaller surges, lightning arresters are designed to handle much larger, instantaneous electrical surges generated by lightning. Lightning arresters are developed in compliance with standards like which provide specifications for their design and application in high-voltage systems. Working principle of lightning arrestor. A lightning arrestor, LA, is a protective device installed in electrical power systems to protect equipment such as transformers, circuit breakers, generators, and transmission lines from the damaging effects of lightning strikes. Under normal operating conditions, the lightning arrestor behaves like an insulator and does not allow current to flow to the ground. When a lightning strike or a very high voltage surge reaches the power line, the voltage rises above the arrestor's protective level. At this point, the arrestor immediately changes from a high-resistance state to a low-resistance state, providing a safe path for the surge current to flow directly to Earth. This action diverts the dangerous surge away from electrical equipment, preventing insulation failure, flashover, and equipment damage. After the lightning surge has passed and the system voltage returns to its normal value, the arrestor automatically restores its high resistance state and stops conducting current. Modern lightning arresters commonly use metal oxide varistors, MOVs, made from zinc oxide, which respond within microseconds without requiring spark gaps. Working steps. Under normal voltage, the lightning arrestor acts as an insulator. A lightning strike creates a high voltage surge on the power line. The arrestor senses the excessive voltage and becomes conductive. The surge current flows safely through the arrestor to the earth. After the surge disappears, the arrestor returns to its insulating state. The power system continues operating normally without interrupting the supply. Working principle of surge arrestor. A surge arrestor is a protective device designed to protect electrical and electronic equipment from transient overvoltages caused by lightning, switching operations, capacitor bank switching, motor starting, or internal electrical faults. During normal operating conditions, the surge arrestor has very high electrical resistance and does not conduct current. When a voltage surge exceeds the arrestor's rated protection level, the nonlinear metal oxide varistor, MOV, inside the arrestor rapidly changes to a low resistance state. This allows the excessive surge current to be diverted safely to the grounding system instead of passing through sensitive equipment. The voltage across the protected equipment is limited to a safe level, preventing insulation breakdown and damage to electrical devices. Once the surge has ended, the MOV returns to its original high-resistance state, and the surge arrestor resumes normal operation without affecting the power supply. Surge arresters are widely used in residential buildings, industrial plants, substations, communication systems, control panels, solar power systems, and sensitive electronic equipment. They protect against both external lightning surges and internally generated switching surges, ensuring system reliability and extending the service life of electrical equipment. Working steps. During normal operation, the surge arrestor remains non-conductive. A transient overvoltage, surge, occurs due to lightning or switching. The MOV inside the arrestor becomes conductive within microseconds. The surge current is diverted safely to the grounding system. The protected equipment receives only a safe voltage level. After the surge ends, the arrestor returns to its high-resistance state and normal operation. Different installation locations. Lightning arresters are generally installed in primary systems to prevent the direct intrusion of lightning waves and protect overhead lines and electrical equipment. SPD surge protectors are installed more on secondary systems and serve as supplementary measures when the arrestor has eliminated the direct intrusion of lightning waves or when the arrestor has not completely eliminated the lightning waves. Therefore, lightning arresters are often installed at the entrance. SPDs are often installed at the end of the line or signal loop. Different materials. The main material of the lightning arrestor is zinc oxide, a type of metal oxide varistor, while the main material of the surge protector varies according to the surge resistance level and graded protection, and its design is much more precise than ordinary lightning arresters. Nominal discharge current. For lightning arresters, nominal discharge currents in range from 1.5 kV, 2.5 kV, 5 kV, 10 kV to 20 kV. These are based on an 8/20 microseconds nominal lightning current. For surge protectors, nominal discharge currents range from 5 kA, 10 kA, 0.5 kA, 20 kA, 30 kA, and can reach up to 1 to 0 kV. Testing standards and requirements. The testing standards and requirements for these two devices are quite different. Because lightning arresters are connected to the primary electrical system, they need to have excellent external insulation properties. This often results in a larger size. Surge protectors, on the other hand, are connected to low voltage systems and can be made much smaller. In terms of appearance and size, lightning arresters are usually made of silicone rubber, ceramic, or metal cans, making them larger and heavier. Surge protectors often use small amounts of silicone, epoxy encapsulation, plastic cases, and combinations of metal and ceramic or metal and plastic. Usage. Lightning arresters are primarily used in power stations, power lines, distribution stations, power generation, capacitors, motors, transformers, neutral points, steel making, and railways. Surge protectors are mainly used in low voltage distribution, cabinets, low voltage appliances, communication, signal, workstations, and server rooms. Conclusion. The nominal discharge current, in, is an important parameter for both surge protectors and lightning arresters. For surge protectors, this parameter is defined as the peak value of the current through the surge protector when it is subjected to a 8/20 microseconds waveform impulse current injection. The standard nominal discharge current values are 5 kA, 10 kA, 20 kA, 40 kA, and so on. The nominal discharge current value chosen should match the expected surge current level in the application. For lightning arresters, the nominal discharge current is defined similarly. However, these devices are designed to handle much higher surge currents than surge protectors due to their typical application in high voltage power systems. Therefore, the nominal discharge currents for lightning arresters are significantly higher than those for surge protectors. To summarize, while surge protectors and lightning arresters serve similar purposes of protecting electrical and electronic equipment,